Alrighty, nerds, we're going to start the last section of Precalculus knowledge. This is going to be Unit 2.15, going to take a minimum of 2 lessons. We'll see how far we get. And I think it's very important that you understand that this stuff that we're about to do is brand new to the Precalculus curriculum. You know, AP Precalc just rolled out this year. Semi-log plots are brand new to Precalculus. They did not exist in Precalc Honors. They're not in my other textbook. This is brand new information. In fact, the very first time I've ever taught it was today, second period. I've never taught it to students, ever. I'm going to need you to pay close attention because their scaling is strange. Semi-log plots are a useful tool for visualizing data that covers a wide range of values. Literally, the range could be way too much. A semi-log plot is a graph that combines logarithmic scale for one axis with a linear scale. Linear scale for the other axis. It is used to plot data that covers a wide range of values where a linear plot would make it difficult to see the details. Believe it or not, this is a linear plot. But Mr. M, I've graphed quadratics before. Those aren't linear. You're correct. But your axes were linear. Look, they increase and decrease at a constant rate. They are linear. Even if they went by 3s, 3, 6, 9, 12, that's still considered linear because it's arithmetic. So you've never graphed anything on axes that were not linear. But linear things don't always show us very good detail. For example, if you try to graph exponential growth, first of all, there's nothing down here. And second of all, let's just use a nice base, like a nice small one, 2 to the x. You get 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is already off the chart. And that was with a nice small base of 2. If the base is worse, like 3, you get 3 to the 1 is 3, 3 to the 2 is 9, already off the chart. You see, exponential things grow really, really fast, a wide range of values. The semi-log plot will create a graph that reveals the details of this data while still showing your overall trend. So in this lesson, we will learn how to create and also interpret semi-log plots. Example 1 is very simple. This is the line y equals x. Its data is linear. You see all the x's are increasing by 1, all the y values are increasing by 1. It is linear. So all we have to do is put a dot at every one of these coordinates, connect the dots with a straight line, the line y equals x. And do your best to connect them. There, they're connected. Yay, y equals x. Easy peasy. Now, we don't have a problem seeing all of the data values on this graph because it's a linear function with a linear scale, no big deal. But what happens if we take our linear data and use this semi-log plot? Notice, please, that the y-axis has a very strange scale. The x-axis is still linear, it's still counting by ones. But look at this y-axis. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. What you're supposed to be seeing is that the closer we get to a power of 10, the more compressed the data becomes. From here to here are all multiples of 10 to the negative 1. Here's 1 times 10 to the negative 1, 2 times 10 to the negative 1, 3 times 10 to the negative 1. That's 5 times 10 to the negative 1. Here's 1 times 10 to the negative 1. Everything after that are multiples of 10 to the next power, the 0 power. Because 10 to the 0 is 1. So here's 2 times 10 to the 0, 3 times 10 to the 0, 5 times 10 to the 0, 10 times 10 to the 0. How about that? You could also say that this value right here is 1 times 10 to the 0. So you can say 1 times 10 to the 0 or 10 times 10 to the negative 1, whatever you want to say. It says use the semi-logarithmic axis at right to plot the graph y equals x. Well, we can't do any negative x's because our grid begins at x equals 0. Our first coordinate would have been 0, 0, and shucks, shoot, darn, 0, 0 does not exist on this graph. So the next thing we could do is 1, 1. 1, 1 is here. Then 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And you know it would go through 7, 7 as well. What is going on, right? What's really going on? Well, if you were to connect these dots, what do you see? A logarithmic graph. It says, notice that the vertical axis is a logarithmic scale, which is base 10, which I showed you. So there are no negative values for y since we can't find the log of a negative number. Horizontal axis is still linear, like I said. It says, what do you notice? And you guys noticed it right off the bat. The graph appears logarithmic. Ta-da! Before I move on and read, I'm curious if there's anybody in the room that outside of their math class has seen a grid that looks similar to this. In physics? Oh, in physics you might have seen intensity of light? Maybe? Yeah? So like star brightness? Yeah. And that's when you see that straight line and it shows you, or like you've got that column where most of your stars fall within the channel, right? Yeah. Anybody else seen it somewhere else? And the reason why is because light intensity is logarithmic. Anybody else seen something like this before? I know that people that play instruments have seen something like this before. Yes, you have. Yes, you have. In fact, it's on a poster in the band room. Okay, people that play instrument for the school then. Okay, anybody in the room play a string instrument? What does this look like? It looks like the frets on a guitar, doesn't it? It's not an accident. No, it's not really specific because all notes are logarithmic. They're separated by fifths, are they not? A, B, C, D, E. These are separated by, these are called fifths, right? Well, but they are. Just so you know. Musical notes are logarithmic. And what you're looking at here are octaves. Isn't that neat? Goes to show you that math was not invented. It was created by the universe. No, it was discovered, but it was created. The universe is mathematical. Now, we don't know why. It just is, clearly. I mean, why do the musical notes sound the way they do to us? Why do we say that that's an A and that's a B and that's a C note? They just sound whole to us. They're logarithmic. And when we learn some more trigonometry, I can bring this back up to you, but sound has a wavelength. The wavelength of a B note is exactly half as long as the wavelength of an A note. A C note wavelength is exactly half as long as a B note wavelength. They're log base 2. You did your physics IA on what? On wavelengths.
And I got into the science bit.
Cool beans. But you didn't do it for music?
No, well, because I play violin. Like, that was my connection.
Nice. Nice, yeah. Violins don't have frets, but the notes still land the same way. Yep. So cool, huh? There you go. Okay. Mathematically treat a logarithmic axis as a transformation of the variables. For our course, we're going to plot data pairs x, y's, and semi-log plots working with log or natural log. It says of the y values. I'm concerned, though, that we could also see semi-log plots where the y is linear and the x is logarithmic. Don't worry, it's done exactly the same way. You just take the log of the x's instead of the log of the y's, or the ln of the x's instead of the ln of the y's. It doesn't really matter. Again, a logarithmic scale is great because it will compress a large amount of data into a smaller area. So this semi-log plot is showing us multiples of powers of 10. Here, these are the multiples of 10 to the 0. Because 10 to the 0 is 1. So these are the 1s. These are multiples of 10 to the 1. These are the 10s. So this is the numbers 1 through 10. This is the numbers 20 through 100. So it's like this is 20, this is 30, so on and so forth. This is 10 to the second. So this number here is 200, this is 300. These represent the multiples of 10 to the thirds. So here you have 2,000, 3,000. And then up here, you've got your 10 to the fourths or your 10,000s. So this is 20,000, 30,000, so on and so forth. Here, we have data from the function 9 times 3 to the x. 9 times 3 to the x is, well, steep. Okay, its y values grow very, very quickly. Very quickly. I mean, 3 to the x grows really fast. Now it's being multiplied by 9. That's pretty crazy. What we're going to do is we're going to plot these x comma y's onto this semi-log plot where the y-axis is logarithmic, powers of 10. Okay, log base 10. Let us see. 0, 9, that is here. 1, 27. All right, that's almost 30. So about there. Two, 81 is just a little bit over 80. Three, 243. That's almost right between 200 and 300. If you make your dots fat, no one can argue with you. You're like, yeah, I hit 243. See? The next number is going to be a little bit after the number 700. Oof, that one's tough. 1,000, 9, 8, 7 is here. So a little bit after 700. Make your dots fat and it's hard for people to argue with you. That number is just a little bit more than 2,000. This one's halfway between 6,000 and 7,000. So this is 3, 4, 5, 6 and a half. Almost 20,000. And lastly, almost 60,000. So this is 30, 40, 50, 60, almost 60,000. Look at that string of dots. Them bad boys are linear, aren't they? So what did we notice about the graph of an exponential function when it's put on a semi-log plot? It makes the graph appear linear. This makes exponential data appear linear. Turner. C wants to actually know what is the linear equation then. Get it into mx plus b format using log base 3 of both sides. Fine. Easiest way to do this is to expand the logarithm. Because I have a multiplication in the argument, I can say that this is log base 3 of 9 plus log base 3 of 3 to the x. What does log base 3 of 9 equal? We should all be able to easily identify that. 2, because it says what power of 3 gets me a 9? 2. And what happens here? I could move the x to the front, or I could just do this and allow the x to fall down. Either way, I'm going to get x, because log base 3 of 3 is 1. But this allows the x to fall down. Remember, like the glue bottle falling off the stool? It did say to write it in this format, though, so I'm just going to rewrite it. Log base 3 of f of x equals x plus 2. We can now identify our slope and our y-intercept, quote unquote. We have a slope of 1 and a y-intercept of 2. So a slope of 1, that means I'm going up 1, right 1. But that means my y values are increasing by 1. So log base 3 of f of x is 1. Meaning I'm tripling every time. So every time I go up by 1 on my y, I've tripled my value. Which should make perfect sense because every time this exponent increases by 1, you multiply by 3 again. It says to plot them. Okay. Crosses at 2, and then it's got a slope of 1. Eek. So difficult. But what's important for you to understand is that this is not the x, y axis. This is the x, and this is not a y-axis. It's actually log base 3 of f of x axis. So every one of those y values is actually log base 3 of the true y value. For example, right here, this says log base 3 of our y value gives me 3. So you put a 3 here, use exponential base 3 on both sides, you find out that your true y value there is 27. Your true y value is 27 when x is 1. Hey, look! Can you guys handle that? A semi-log plot takes exponential data and straightens it out. That way you can fit more stuff on a graph. But that means every increase on the y-axis is actually you multiplying by whatever the base was. We have 8 times 2 to the 2x. We're going to find the y-intercept and the slope of the linearized, which is actually the word for that, the linearized graph. Then we're going to graph it. And it says label the axes appropriately. Okay. First, log base 2 of both sides. Just like before, you're going to want to expand your logarithm. And just like last time, we can evaluate this. What does log base 2 of 8 equal to? It is equal to 3. And just like last time, log base 2, going to cancel exponential base 2, dropping down my 2x. So then what is our slope? The slope is 2. And the quote-unquote y-intercept is 3. So if you wanted to graph that, starts at 3 and goes up to right 1, up to right 1, up to right 1, and connect dots. But that's only if this is the x-axis and this is the log base 2 of g of x-axis. Ta-da! That means every time you go up by 1 on the y-axis, you've actually doubled the y value. That means if you have to go up by 2, you quadrupled your y value. Which should make sense because this says 2 to the 2x, which could have been read as 4 to the x. And that's why we're quadrupling every time we go up by 2. How do you feel? Is it scary hard yet? Honestly, I feel like plotting things on Simulog plot is the hardest part of today's lesson. Reading the Simulog plots in the future of this unit is, again, I think tougher. At least it is for me. It's harder for me. Here we have an exponential that has the natural base e as its exponential base. And it wants us to do the same thing. But instead of using log base, whatever the heck we want to use, we're going to go ahead and use the natural log because we're trying to cancel the base e. Okay? Let's see. What's a good color? Let's use the natural log of left equals natural log of right. And just like before, because there's a multiplication in my argument, I'm going to split that into the addition of 2 logarithms. So the natural log of 5 plus the natural log of e to the 7x over 3, and that is what I get when I take the natural log of h of x. Could you evaluate the natural log of 5? Yes, you could. It's like 1.6 or something like that, ish. It's not pretty. Over here, though, so I get that the natural log of h of x is, and because we want it to look like mx plus b, I'm going to write the part with x first, and I'm not going to put the x in the fraction. I'll put it next to the fraction. And there it is. So if you wanted to identify them, you can say that m is 7 over 3, and b is the natural log of 5, which is about 1.6-ish. I think. Pretty sure it's 1.6. Is it? Yeah, it's about 1.61. So. We don't need to graph that one. I hope you don't think it's that bad. I hope you're looking at it going, oh yeah, it makes sense. This one is once again a natural base E question. What we first need to do is figure out what the natural log of these 5 y values are. So we've got the natural log of 3. If you round it to 3 decimals, it's 1.099. Natural log of 8.2 is about 10.104. Oh, I forgot my parenthesis. Bad mathematician. Natural log of 22.2 is around 3.1. Natural log 445, about 6.098. And lastly, the natural log of 66079, about 11.099. You know, if you wanted to find the average rate of change over this whole table, you know it would just be the slope between these two coordinates, right? But look at what you get when you subtract your y values. This minus this is exactly 10. And your x's are 20 minus 0. And 10 over 20 is 0.5. So this line has a slope of around 0.5. Isn't that interesting? It says find a linear regression model for the graph. Now we could do this by hand. You could, and you would have to use the average rate of change. But no, we have technology, baby. So we're going to come down to a stat and hit edit. And oh, look at that. My table's already filled out with that information. So you want to put the 0, 2, 4, 10, and 20 on there. And then you want to put these 5 numbers in for your y's. And I'll pause the video while I wait for you guys to do that. Now that we've all got them typed in, the question says to find a linear regression. So stat, calc, scroll down to linreg. Let's be really clear here, not ln reg, not the natural log, a linear regression, ax plus b. Slope-intercept form. And because I don't look ahead normally to see if I need to store it, I'm just going to go ahead and store it just because it's good habits. Vars, y vars, function y1, and hit calculate. And hey, remember what I said the average rate of change was? I said it was 0.5. Look at this thing's slope. It's almost exactly 0.5. I mean, look at these regression numbers. It's almost perfect linear regression. Almost perfect. Y hat is 0.4999. I'm going to go out to 4 decimals x plus about 1.101. And it says use your calculator to find the linear regression model to verify your equation. Oh, that's stupid. That's what I just did. Oh, I see. I see. This one I was supposed to do it by hand and get the average rate of change was exactly 0.5 and then say that this is the y-intercept at 1.099. That's what I was supposed to do. And I have them backwards. So this is the true regression. This is the tech regression. And if you want to do it by hand, then you would have to find the slope, the average rate of change, which would have been 11.099 minus 1.099 divided by 20 minus 0, which is 10 over 20, which is exactly 1/2. And your y-intercept is happening when t is 0, so it's happening right there at 1.099. So this one's equation would have been y hat equals 0.5x plus 1.099, whatever. Now let's graph it. Let us graph it. Technology, all the way, for real. 0, comma, hair above 1. Don't you do it. I'm about to get kicked out of gradebook. There we go. 2, comma, a little bit more than 2. 4, comma, 3. 10, comma, a bit past 6. 20, comma, a bit past 11. I mean, look how straight that is. It's almost perfect. Almost perfect. So neat. Now, in all actuality, the true equation, instead of saying y hat, the true equation that we've built here is the natural log of y equals either the one that the technology gave us or the one that we got by hand. It doesn't really matter. Doesn't really matter which one we choose, but they are both the natural log of y. We good? Okay. I think that that's a great place to call it right there. It feels good. Oh, you know what I just realized? Small mistake here. This can't be my b value. The b value is the natural log of 0, which should have been, that didn't make any sense. Never mind what I'm saying. No, we did it good. Look, I'm gonna stop the video before I do something stupid.